Welcome to another live stream. Today I'm going to complete the refactoring of the Jupyter notebook for which I've migrated the notebook from Kaggle to Google Colab. For anyone new to the stream, right? I've been working on training a new image classification model for a Raspberry Pi camera, which I have deployed in my back garden. And this new classification model, I've trained it to detect 3 types of animals that I get mainly: a cat, and a fox, or a bird, right? So I've spent quite a lot of time actually gathering a new data set and then also experimenting with different combinations of images. So I gathered a data set from the internet and from other data sets on Kaggle, and I also experimented. I've also gathered my own images. Okay, so I'm almost done with this, to be honest, right? So at this stage, right, I've already managed to do the end-to-end. So I'm using transfer learning. I'm gathering a data set of my own. I've already uploaded the data set on Kaggle. I'm doing transfer learning. I'm using MobileNet as the model, the pre-trained model that I'm using from the Tensorflow hub, and then I'm applying on top of that model. I'm doing transfer learning and using my own data set. Okay, yeah, at the end I'm converting it to TFLite, and I'm converting it to TFLite so I can use it either directly on the Raspberry Pi, or I can use it with I have one of those edge TPUs that Google provides. I bought one. It's supposed to be faster. But actually, I found that just the plain TensorFlow-like model on the Raspberry Pi 4 is more than enough. Anyway, so today I'm going to complete this refactoring of the notebook. I'm almost done. The only thing I'm missing now is the code that actually converts the model to TensorFlow-Lite. After that, I'm probably going to just tidy up some documentation in the notebook so that anyone can follow what I've done here, and then I'll discuss the next steps closer to the end of the live stream. And if you need to interrupt me, feel free to ask any questions, and I'll be more than happy to answer. Without further ado, let's get started. Okay, so this is Google Colab. I'm going to run this notebook. I think I need to actually upload first my own keys first. So because I'm actually downloading a dataset from Kaggle, I need to upload my own Kaggle key. Going to run this cell, which will install Kaggle and then also move the file I've just uploaded into the right directory so it picks it up. Just try and make this a bit bigger. Easier to just do Ctrl+, so it's very big. Okay. I've installed Kaggle. Now I'm going to download the dataset. It's actually a big one. So almost 3 gigabytes, more than 3 gigabytes. downloaded quite quickly actually. Now we have the data. It's just extracting the data set and placing in the right location. It looks okay. I don't think I need this cell anymore. So this cell is just telling me which version of Tensorflow we are using in Google Colab. 2.8.2. Now I'm just downloading some definitions of functions I had to create. It's a function to square an image without cropping. It's actually using padding. So function here to copy files. So what I'm doing here, I'm copying images from the source, which is in so I copied it to Kaggle input, right? So I'm copying images from Kaggle input into Kaggle working. And what I'm doing, I'm also at the same time resizing the images and with padding here, so that we can keep the aspect ratio. Because we have to square all the images. The model, the pre-trained model we're using needs square images. Okay, so now I'm just going to run this. So I'm also deleting, adding some comments. It's huge. So the idea is we have another, we have 3 classes of animals, right? We have cat, fox, and bird. But then I also added another class called empty, right? Because I thought that maybe it would be useful to, if I give an image of my garden, there's nothing there, it should just say empty. But then I realized, okay, actually maybe I don't need to do that, because I'm going to just use, I'm going to have an architecture I'll explain at some point later today. The idea is before I even call my image classification model, I'm going to use an AI toolkit of some sort to actually check first whether the image contains anything, just using a out-of-the-box pre-trained model. Yeah, it should at least tell me if there is anything there that has life, like a cat, a dog, or a person, it doesn't matter what it is. Once I know there is something there, then I'll apply this image classification model, and that's why I don't think I need the empty model, the empty image class, because yeah, but maybe in the future it might be useful, so I didn't delete it from the dataset yet. Okay, so that's what we're doing here. And then we also check, and at the same time as I'm explaining you what the notebook is, I'm also adding some comments, because I think it's needed, right? So now oh man, for each image class. So now we check how many images we have for each image class, and you can see we have, so this is for, so I have 2 types of dataset I gather, one dataset from the internet and one from my garden. Okay, and the last one is a test dataset. This is also from my garden, but they are, so these 2 are separate. I've gathered from different videos here. So you can see the ratios are more or less similar, right? We have almost 500 of each animal. It's a bit different for the my garden dataset because I didn't have as many birds to I didn't have that much data there for birds, but I had for cats and fox. And then the same, yeah, so the same thing for the test dataset. I probably should have something like a print statement saying just going to copy and paste this print statement just to have some more. I call it my garden dataset because that's how it is. It's from my garden. And then we have test dataset, which are also from my garden. It'll be a bit easier to read, right? Okay, now it's a bit better. Okay, so here, this code is just to allow us to see what's in our data. So you can see, and this is how, you see, this is a fox, right? But notice something peculiar about, this is from the internet dataset, the fox in the center, well in view, okay. You'll notice that we also square the image and we have black bars. Okay, we have now the fox, another fox here. Also from the internet dataset, I gathered. Also well in the center, more or less clear view. So someone probably took a picture of it. So the birds are most the same, yeah, they are very clear. This cat looks a little bit surprised. Right, okay. So this code now is basically image dataset from directory, yeah? This is a very important method in Keras that you probably use a lot if you're trying to do image classification, because it makes your life a lot easier. Basically, it takes images from a folder, okay, right, and maybe I should show it. It's easier to see. Let me just go. Yeah, let's go up. So if I go to Kaggle, which is where I put all the images, yeah, it can be done here or here, right? You'll see this is our data set, right? So we have internet data set, the my garden data set, and the test data set, and each data set has 3 folders, and each folder is basically a label that we are detecting, okay? And with this method here, image dataset from directory, we are basically creating it basically automatically creates the different labels for us, so we don't have to tell it what each label is. It will create basically a category for each folder. Okay, it also does much more, right? For instance, it basically can mix things together, right? All the images, it shuffles them if we want to. Also, it will allow us to retrieve images by a batch size, which is important when you're training a model, So in this case, the batch size is 32. And then we also can resize the image if we want to. In our case, we've already resized the image for other reasons, because I didn't want to, okay, I don't even have to, I mean, this is irrelevant now, right? But the reason why I didn't want to resize through this method here is because the only way you can resize mainly is by cropping, and I didn't want to do cropping. Okay. So let's see. Okay, so this is where the training actually starts, right? So so this is just loading the data into a data set. Okay, there's more cells actually. Here we can see, okay, this piece of code is basically giving us an overview of what is in our internet dataset. Instead of just showing one image, we show a number of images. Okay. All very easy to tell what they are. Okay, there's a label here as well. It's a bit small, the letter, but it tells me the ground truth here. This is a cat, and so on. Okay, this code is basically just identifying shapes. Shapes are very important, right? When you're trying to use TensorFlow and tensors, you need to know your shapes. So here we know this is a batch size of 32. So we have here, this is the shape, first dimension, 32. So 32 images. And this one is for the size of the image. It's 224 pixels square. Okay. And then 3 is the number of channels. Thank you, Dark Matter, very kind comment. If you have any questions, let me know. I will be happy to answer. Okay. So in this notebook, okay, so another thing that the image dataset from directory does is to actually load images. So you can actually create your test dataset. You can create your training dataset and your validation dataset, and you can use the validation split here. Okay, let me see if I understand your question, Dark Matter. Right, when you download it, you're talking about downloading what? The images? And which folder and file you should code with? Okay. Can you clarify what you mean downloaded? Yeah, I think there is a delay, so you might only hear me like 30 seconds later. By the way, I copied, I published this gist on GitHub, so you can actually open it if you want to follow this. Okay, so I just let me know if you can open it. And I just realized I was working directly on the gist itself, which is fine. Okay, right, so okay, you can clarify your question. I'll continue until I understand your question better. So we have here image dataset from directory, and it can basically load the data into and split it into training and validation. Okay, and that's what I'm doing here. Okay, so you can see that it has loaded 1,180 images for training. Okay, and this is 80% of the data. And I know this is for training because I specify here subset equal to training. and here we specify subset equal to validation. Okay, and now I can run this for my garden dataset. I've also added here the garden dataset, and I did the same thing for splitting this into training and validation. So I was working on Kaggle before, right? And the problem with Kaggle is that it's running a version of TensorFlow which has a bug, and that version of TensorFlow, well, it was really annoying. That error was showing up everywhere, so I had to move to Google Colab. Okay, so in Google Colab, I created the last live stream. I created this notebook, and just before I started, I published the notebook I was working on as a gist in GitHub. Okay, and that this is what you have in terms of like this model I've created here, right? This is just the starting point because I actually need to gather more data, right? So, but I only can gather more data once I deploy this model onto Raspberry Pi, and I'm planning to also create like a pipeline to get more images so I can use feed it back into creating a better model. Okay, right. So I'm going to just keep running these cells until we get to the end. More or less the same. Okay, here is where we actually starting the training. We are creating, basically we are picking our classifier model. For now we only use MobileNet. There's Inception version 3 here, but I think Inception is too big for it's a very powerful model, but it's probably too good for what I need. So I'm not using it for now. Okay, so now we are building the model. So we are doing transfer learning, so we download the whole model, but then we remove the top layer and we keep the weights as well. And then because we're doing transfer learning, we also make sure that the weights of the layers that we keep are not going to change. So we set base model to trainable equal to false, so the weights will be static. And then this is continuing building the model. We're adding some global average pooling to and then we also add a dense layer. We should have also dropout somewhere. I don't see it here. Oh, the dropout is here. This is a type of regularization. We're trying to make it harder for the model to memorize everything. So we want to force the model to kind of only learn the things that are essential about the images, like what the fox is, because if you allow the model to overfit, it will basically just memorize every pixel, and it's not good. Okay, so we have a learning rate, and now we're just building the model again. Yeah, we're just checking the training variables, and this is where this piece of code is just doing an evaluation of the model without doing any training. So we expect the accuracy to be very low. Okay. It varies as well because this is a GPU. GPUs are known to be non-deterministic, right? So don't be surprised if getting different accuracies every time you run this. Having said that, now it's giving the same result, but never mind. Okay, now we are actually training. So the reason why we would use, okay, so dark matter is asking why would we use transfer learning instead of another type of training, and how would we figure that out? For me, it's the easy answer. First of all, I don't have enough data, right? So I only have like a few hundred images from my own garden, right? And even though I could collect a million images from my garden, to be honest, but then the problem is they are not very like they're almost all the same, right? And then it's not going to be easy to train a model from scratch with that amount of data, right? So that's why I'm using transfer learning, because we can use a model that has already learned on hundreds of thousands of images, and we can just it basically is a model that already kind of can see things. It's able to distinguish features, okay? And this is a key bit, right? Features. It can, for example, if you tell it, okay, it knows what an animal is or what a leg is, or because it has already seen thousands and thousands of images with legs or with animals, right? So that's why we use the model. Even though it doesn't know how to do the specific task we want it to do, it can easily learn with a little bit more data, because it already has done the hardest part, which is to learn how to see. So transfer learning is often used just because it's expensive to train a model from scratch, and quite often you don't have that much data. So if you don't have much data, you don't want to be training something from scratch. So that's why I'm using transfer learning. Okay. All right, so we have here some images from our test data set. Okay, this is actually trained already, right? So yeah, we've trained the model only using images from the internet, okay? Without looking at the images from my garden, okay? And we got, so you can see it was able to achieve an accuracy on the validation data set of 96%, okay? And when you apply this model to the validation data set, right? And this is an example. Okay, sorry, it's very small, but in general, this model is very good at basically, with the pictures that I've gathered from the internet, it's very good at knowing what's inside there, right? And I think this is because this is very similar to the type of images you see in ImageNet, the dataset, taken by people. Always you see the subject in the center, they are clear, so that's why it's very good at distinguishing it, okay? But the problem is, this is nothing like my own data set, and you'll see the difference here. In fact, you can already, I'll show you in a second. Okay, we can see here also some graphs that these are functions, okay? So, okay, at this point, okay, this is just to calculate accuracy. You can see, so the model.evaluate is doing basically the same thing. So this number here that you get is similar to the one we got at the end for the training, okay? Because we are doing model evaluate against the same validation data set, so this number is going to be very similar to this one that we calculated here, okay? Right, so it doesn't tell us much, to be honest. But okay, at this point in my notebook, I'm actually going to create some functions, okay, with the code that I had before. And the idea of having all these functions is so that I can do some experiments with the data, just making changes to the data sets and swapping things around. Okay, actually this is not sure. I think this is wrong. Okay, myself. Just notice a bug I had here. I was looking at the wrong data set. Okay, right, so now let's see, predictions. So this is another function I created, and now we can, okay, so now we can do experiments. So you see I defined a few functions, and now I'm using the functions I've defined, and instead of just like copy and pasting the code as I was doing on Kaggle, which was very cumbersome and not very practical, here I can just specify, okay, train model, and I'm saying, okay, my first argument is the training data set, the second argument is the validation data set, and the third argument is the test data set, okay? Here the names actually match quite well, okay? But actually I can pass in the test data set as a training data set. I can do anything I want, right? Because the function here that I've defined says that the first argument is the training data set, the second argument is the validation data set, and the third argument is the test data set, okay? And then these ones are extra arguments. Okay, let me see a question. Okay, so Dark Matter has another question. If I would like to create an image data set, how would I scrape the images of cats and dogs from Google Images and then implement it into the model? There is ways to scrape the images if you use a Python script. I've done that before. Actually, I've created, for example, I remember when I did the image classification model for images from the nativity, I had to scrape images from like websites with paintings. So you can create a script. Quite often you'll find that, well, as a data scientist, you'll have to create scripts to scrape data because it's much quicker. And then basically you normally, it's a good practice to remember where you download the images from. So you can create a CSV with the URLs of the images and the sources that you have, so you can remember, you know, it's important sometimes for copyright and whatever. And then you can save also the image separately. I found out that from experience, right, if you only download the URL, if you only keep the URL in the future might not work. So you probably want to keep both. Yeah. So that's how you do it. You just create a Python script. Alright. Okay, so let's run the first experiment. So the first experiment I'm doing here is training the model using a data set that was gathered from the multiple searches from the internet, okay? So we are using internet data set for training, internet data set for validation. And here, this test data set is actually from my own garden. And to be honest, I didn't show how that looks like. I probably should have somewhere here a view of that data set, just to show you how different it is. Okay, let me just copy and paste. Code. Let's use training, it doesn't matter what it is. Okay. Okay, you see, this is my garden dataset. It's very different, right? I know there is a fox somewhere here. Okay, the fox is here. See, you barely can see it because the image is tiny. But then you have a cat here. This is nothing like the images you get from the internet. Okay. So the first experiment. What is it? Okay, the first experiment is basically, I'm using the training, well, this is the same data set from the internet, okay? And then the test data set is from my own garden, okay? And this is important because I actually want to deploy this model in my garden, right? I don't want to deploy it on the internet. And you'll see the results are not great. So we're only training 10 epochs, but you'll see the accuracy for the training dataset that normally goes up. A model normally doesn't have any problems fitting to the training dataset, so unless something is really wrong. So the loss should go down and the accuracy should go up. And then the validation loss is the one that's a bit higher, right? Sometimes you will see that the validation loss or the validation accuracy will not go as high as you expect it to go. But in this case, it's no problem because these two data sets are very much, they are very similar. They're independent because we separated the images from the training data set from the validation data set. They are different images, and the model only learns from this data set. And this data set is more like useful guidance. At the end of each epoch, we score the model according to the validation data set, and that helps the machine learning algorithm to decide where to go next in terms of changing the weights and activations. Okay, and you can see here, this is almost like the perfect curve. It goes up, so the training accuracy goes up and validation accuracy goes up. The training loss goes down and validation loss goes down. This is great, this is awesome. Okay, but when you look at the evaluation against the test data set, you'll see that when we evaluate the model against the validation data set, it's 97% accurate. But when we validate it against the test data set, it's only like 30% accurate. And the reason is, even I have difficulty detecting what the image has, right? So the model itself can't understand. It hasn't been taught to identify foxes here or whatever, right? This is completely different. So that's why you have to be careful how you gather your data set. Okay. And that's why we normally have 3 data sets. Okay. Okay, so this is the second experiment. Okay, I realized that, okay, so I'm trying to improve things without really actually, I didn't want the model to learn directly on my data set because I only have like, the same background, right? The background is the same and the fox is probably always the same, who knows? And the cats, they are always the same. Because I have 2 cats coming through my garden, right? They are not mine. There's a black cat and there's a brown cat, that's it. Yeah, so I didn't want my machine learning model to only distinguish those 2 cats. So what I decided to do, I just put the internet dataset as my training dataset, so the actual model will learn from the internet dataset. And then my validation dataset is the garden dataset, okay? And let's see what happens. Oh, and this is an important one here. Early stopping equal to true. This is something that TensorFlow allows you to do, because when you're actually training for a long period, like let's say for 20 epochs, there will be a point in time where, for example, in this case, we are monitoring, I think, the validation loss, okay? Where the loss itself can't go down anymore, it will go up instead of going down. And with TensorFlow, we have early stopping, like a class, and you can specify the tolerance, like how many epochs you want it to wait until things get better. And then if it sees that the loss is getting worse, it will stop training. And this is what's happening here, right? So we've got to a point, okay, the model has trained and it only reached an accuracy of 19%, which is very low. Funnily enough, it does very bad on the validation dataset. This is from my own garden. And then another dataset, which is also from my own garden, it's actually doing better on that. But to be honest, that kind of means doesn't mean much to me. It's just a coincidence. If I run this again, I probably will get different values. Okay, so we have this. Okay, this is not a good result as well. because I think mainly because the images from the internet, they are so different from the images in my garden or from any other security camera, because the security camera is normally static. You normally have animals on the edges rather than in the center. Okay, we have here this method just to see the predictions, and we see some examples of predictions. This is tiny, I need to fix it. This is a bird somewhere here, or it says it's a bird. This is a cat. I don't know if I want this. Oh, that's not. That's a pot. The bird's here, actually, it's correct. It's a cat. It says it's a cat, and it's correct. It says it's a bird, but it's a fox here. Okay, so the accuracy is not very good. Okay, so now we have. Okay, there's more examples. Okay, it's the third experiment. Okay, I've given up on the internet dataset here. And so I just use my garden dataset for training, my garden dataset for validation, and the test dataset, which is independent, but it's from my garden as well. Okay, so I'm expecting to have better results. Before training is already doing quite maybe too well. So you see the validation actually is going up. 67, 68. The loss is going down, so that's good in a way. Okay, at the end, we can see evaluate model after training using validation dataset. Okay, so we see the accuracy on the validation dataset is okay. It would probably have gotten better if I trained for more epochs. But then you see the problem here, right? When we evaluate accuracy against the test dataset, it's actually quite low. It's lower than what we started with, I think. Yeah. No. Anyway, so 0.41. So I think this just shows that I don't have enough images. Okay. I need to gather more. This is when I kind of concluded that. Because it should do well on both datasets, on the validation dataset and the training dataset. Because we have such a big gap, the only reason is I don't have enough data. That's what I think. Even image augmentation will not necessarily. We already use image augmentation, by the way, but that's not enough. Okay, so next, the fourth experiment is we try to train for longer. Here we only train for 10 epochs. And we also do early stopping, yeah. Okay, so you have another question. Oh, so you're talking about the person from Google who claimed what the chatbot had feelings? Yeah, I'm not sure about that, to be honest. Yeah, I think it would be odd. Okay, so you can see the accuracy is going up on the validation dataset, the loss is going down. But you see, the better it does on the validation dataset, the worse it will do on the test dataset. That was the last time I did the experiment. It can be a bit random sometimes. Okay, so we have these two results here. Okay. You can see it didn't really improve much. Improved not much. So this is almost the same result. So here, so I swap things around. So because I think one of the things I realized is that these two data sets, even though I'm splitting them into separate images, because of the way I collected the data, the images, they were coming from the same video file. I think that it was basically almost the same, so we overfitted the model. So that's why in this experiment here, I'm just swapping things around. So I'm using the test dataset as a validation dataset because I know these two are independent. But then the problem is that if these two are not independent, so this is going to score. Yeah, I have a problem, to be honest. And the only way to solve it is to gather more data, which I will do after I continue on this project. Anyway, okay, so this is the point where I'll complete this and I'll just finish off the refactoring I wanted to do because I'm running out of time. I wanted to copy some code from this notebook which was doing the Tensorflow lite conversion and also does an evaluation of the model. So I'm going to do that quickly before I run out of time. Okay, so we have start copying of the code. I also did the confusion matrix. Confusion matrix is actually used to also different view on. Okay, let's see if this is right. This is what. Okay, label batch. Yeah, Google has a lot of technology that they don't show to everyone. They might have a secret project they don't want us to know about. Okay, so let's copy this. Go where I was. Label batch. It's coming from where? Coming from here. Okay, so I can add this piece of code to the method I already have. A huge method, so I need to create a new one. Def create display confusion matrix. Hello. Hello? I'm actually connected to my mobile. I don't know if that works for streaming. I'll find out. Hello? Can you... Wow. Let me know if the connection is okay, and yeah, I don't know how long it will be until my internet comes back. So let me try and continue. And yeah. Alright, so I was doing confusion matrix and I got disconnected from Google Colab. So I think I need to run this notebook again, but I'll run it in one go. Okay, it's still running. Actually, I'm still on the same notebook, so I don't need to run everything again. Okay. So I was creating a method for the confusion matrix. Yeah. Yeah, and I have some arguments here, which I'm going to replace probably later. But for now, I'm just going to copy them as is. Then from here, I'm going to call display confusion matrix. I think it was from here. Okay, so actually I should call it from here. So view confusion matrix. Passing the arguments, label batch, and prediction ID. And I'm going to put the method just closer to the place where I'm using it. Here. It's the notebook, it's running everything again, so it's probably why it's the see which cell it's. It's running this training again, that's why. Oh, let's finish. Let it finish. All right, cool. It's an error here. Okay. I'm going to pick this method out. And put it here. Oh, I thought I had already. Okay, it's the same method. Okay. Right. So it's executed fine, but because Python only shows you the errors when you're actually executing the code, it doesn't mean it worked. Okay, so let's see. Okay, so at this point, once this is finished training, I will be able to call the method I defined in the previous step. Wait too long. So a confusion matrix is basically a table that will allow me to see visually, like whether whether the model is giving false positives or false negatives. Yeah. Okay. Is that? Something is wrong in the method. View confusion matrix. Oh, display confusion matrix. Even the predicted ID, prediction ID is a different. So predicted ID. This is actually it's a list, not a single number. Okay, comes here. Let's try it again. PD. Okay, so I need to import the pandas library because this method uses the pandas library. So I'm going to do import pandas as PD. Clean up some of this debug. It's starting to make it harder to see what's important. So actually the reason why I was printing that before is because the way it works, these are logits, right? And so each row here, this is a a prediction, okay? And you can see in this prediction we have 3 numbers, and each number belongs to a classification label, okay? I think it's alphabetical right now. It's birds, cats, and foxes, right? So birds is the first one, cat is the second one, and fox is the third one. And basically the algorithm works that the highest number wins. So the prediction here is going to be a fox, yeah. And then you can see the labels here, like when we replace those numbers with the fox, with the actual label. So the first one was labeled as a fox. So these are the predictions, okay. I just removed this debug, but just wanted to explain it. Okay, so we have, this is a prediction of a fox. It's so tiny. We still don't see the pandas, because I think I didn't do a display. PD data frame. If I can do a display data frame, you should show the table. Okay, you can see the confusion matrix here. So PV stands for predicted value and AV is for actual value. So in this case, the predicted value was it's quite bad actually, these results here. So predicted value was bird, and the actual value is fox. And you can see, right, that this model is not very good. And accuracy is quite low. That kind of confirms it, right? So normally you want to see numbers like in this line, diagonal line like this. Yeah. But here this confusion matrix is not good. I need to tidy up this matplotlib, make it a bit nicer. Right, okay, so we have a confusion matrix, and now the next piece of code I wanted to, I'll let this run in the meantime. Okay, so I'm going to copy the next code, which is the conversion. So here, this is where we're doing converting the models to Tensorflow Lite. Okay. For now, I'm just going to copy this as is. Oh, I'm in the wrong place. Okay, here. It's probably not going to compile, but it's still running the code here. Okay, in the meantime, I'm just going to add some text. So basically, at this stage, I'm already saying I want to convert this model to TensorFlow Lite, and this is where it's going to create the file that you could actually copy and use it in a Raspberry Pi. Okay. Give the code. Well, event. I'm going to refactor this also into a method so we can use it for any model we want to convert. just dumping the code here. We put everything to the same cell. Don't mind we make this nice and tidy. Yeah, we have most of it. Let's see. Yeah, okay, I need to open the window. Fine, that's okay. It's a bit hot. It's actually finished running everything, almost. We've done all the experiments, and then now it's time to convert everything to TensorFlow Lite. So this is, so I can actually define a method. Let's call it, for now, naively convert model to TFLite. Yeah, and I just pass in the model, and then we return a TFLite model, something like that. Yeah. So I'm just going to start copying the code. Okay. So first thing we do is call the TFLite converter from Keras model, and then we have a converter, and after that we just call convert. Simple as that. This is actually, I think this, if I'm not, if my memory serves me right, this is actually the normal TensorFlow Lite model. This is the one that you can just use on the Pi directly. Okay. It's not fully quantized. It's not fully quantized. It doesn't. It still has some floats in it, right? So it has been optimized, pruned, but it still uses floats for the weights and activations. If you want to use the full quantized model, and this would be needed, for example, if you were trying to use an edge TPU, then you have to use a second method, which are. That's why we don't have just one method for converting to TensorFlow Lite. We have two. We will have two. Oh, let's call it quantized TF. So normal TFLite, and then quantized. Maybe I should have a better number on. Yeah, fully quantized TFLite for now. That's okay. That's the name. All right. So this code I don't need here. Okay, so everything has been executed. Okay, so this code here is creating some directories. So let's just make this a bit more tidy. Okay. So this is going to be the directory which is going to be our destination, right? Destination folder, right? Going to be the model, and then destination folder, yeah. And then I can replace this ugly string with a variable destination folder. For now, let me initialize this outside so I download it. I'm going to make it different because this is a variable, not a parameter. Okay, we have destination folder. We're creating the directories if it doesn't exist, encoding the parents. Okay. Okay. Then here, this is the name of the model, so we can, let's use a variable here, just say model name. Okay. Make this an F string. So with an F here, I can actually pass in a variable inside the string. This is very useful. So you can just, yeah, I define my strings like this all the time, because then I can just use variables with curly brackets. It's much easier than trying to concatenate the strings together. Okay, so model name can be my another parameter. I have to call it model name for now, it's simpler. So model name, yeah, and then the TFLite can be something, it's a suffix that we add. Okay, and that's it. We return, maybe we can return the file name, or we can return the model. I think we can return a model, it can be easy. Just run evaluations on it, as we are going to do that next year. Okay, so this is the normal TensorFlow-Lite. Now this is the method for the fully quantized TensorFlow-Lite. We'll probably find that there is common code, right? So I might have to, I'll decide what to do with it after I put everything together. So I don't need this. I'll explain this in a second. So we have the same thing, we need a converter, okay? The parameters, we can make them parameters the same. Okay. Convert. And then, okay, so the difference is here actually. We are adding some optimizations. And this is an optimization which is actually new, and this is for the Edge TPU. So we are converting all the weights and activations which are 32 bits in floats, right, into 16 bits for the activations and 8 bits for the weights. And there isn't a complicated algorithm to do this because we're actually going from a bigger data type to a smaller data type. So we need to somehow fit all these numbers in a smaller space, right? So you can imagine that. So what Google actually asks us to define because of that, we need to define a representative dataset method. Okay, and I have to put this probably here. This method is needed so that we can go through. Okay, I need to take all these arguments here. So dataset. The dataset. So the idea is we go through a dataset and we call the inferencing, right? So we do inferencing on a dataset. Yeah, and then the idea is that we try to find other. So it forces basically allows the converter to find out what are the maximum numbers and the minimum numbers within the weights and activations. Okay, so that's why I need to define this. Okay, so we have it can't have arguments, so I'm going to have to define this. Hope you don't hear that. I have to open my window. I have a right, and it might be a bit noisy. Right. So yeah. Then if I can just call it with a map like this, I think I need to pass in. Find this inside this method. You can do that. So this representative data set can be like the test data set or something like that. So data set equal to, for example, I can define default is to test data set. Version. So this is the full code. Need to save to file. So this actually is supposed to be okay. I don't need this. So this is where we are saving to a file, and we can use the same logic as we used above. Destination folder, and then model name. And then we can use also the curly brackets and the F, so we can use the F string. So this will convert the model into TensorFlow, into the fully quantized TensorFlow Lite format, and then it will save into a file name, the file, and then it becomes the model as a variable. Okay. Then this section of the code is it's the code that we use to actually try out the model in TensorFlow in TensorFlowite format. So I'm going to move this to the cell below. We'll try that in a second. For now, let's just read this into a memory. Okay, didn't like that. I need the brackets. Let's try and use convert, for example, a model to TFLite. We can call it, we can use experiment, for example, 5, and just pass in the arguments that we are supposed to pass. Okay, for example, the destination folder, the model name. So let's call, so the destination folder, we can make it content TFLite. Okay, and then the model name, model experiment 5. Let's just call it like that. And then let's see what happens. It's probably going to throw an error, but we'll fix whatever error we get. You should create a folder as well. It takes a bit of time as well. It's not immediate. So the fact that it's actually running and taking a bit of time, it means it's actually already working. But this code here is quite simple, right? Okay. So let's see if there is any. It's nothing great yet, but it's doing something. Any questions so far? Feel free to ask. Okay, so TFLite model is not defined. Okay, because oh, there is a difference in names. Okay. Fix that. I don't need this variable anymore. It should work now. But you see, it already created a folder with the actual TFLite model here, because it only failed in the last line of the method. All right, so dark matter, right now I'm using GPU, but actually in order for you to take advantage of the TPU, right, you need to convert your TensorFlow models to like completely, all the weights and all the activations need to be integers, which is exactly what actually we are doing with the second method. If you are doing machine learning and your TensorFlow models don't actually have are not optimized for the edge TPU, you basically are not getting any benefit. Oh, what happened here? So this is it's returning the model and it's trying to display it as a string. So this is why this is a Unicode. Okay, there's no. Okay, it's worked. Okay, so we have a model here, and the method works, but I didn't want to display all of this, to be honest. Okay, right. So the next step, let's try and call. Next time I run that, it doesn't just try to display it as a string. The TFLite, so model. So this one, oh, didn't mean to run it. Normal. This one is more TFLite. Quantized, or fully quantized. It's here. We share this name. For the second method, it's going to take a bit longer. Same movements. Let's see if there's no errors. Doing the conversion. So what it's actually trying to do in this representative dataset, it's going to go through each image in this test dataset. Actually, I think it only goes through this. Yeah, it goes through all the images in the test dataset, and then it calls the inferencing for it. So it's going to take more time, a lot longer than the other one. Okay. So once we have both models, we can actually we can do some, like, this is the code that you would have on the Raspberry Pi as well. So we can call a special interpreter for TFLite, and then we can do some queries on it. So we already have a method here that runs inferencing on the TFLite model. You see the yielding being called? This is for each batch. So batch of 32 images, because our test data set is like a batch data set which has a batch of 32. This is calling actually the TPU compatible model. Okay, it takes as an argument to the TFLite file. So I probably should have just returned the file name rather than the whole model. So instead of returning TFLite model, I can return this. We have to it's still running this one. Okay, that's why it hasn't created anything. This gave an error. I was wondering if there's something wrong with it. I'm surprised this one even worked. Okay, so path width. Destination folder. Yeah. Trying to figure out what's wrong with it. I think I know. I know what it is. Here I have defined the path width. So you need to call okay. While this is running, now cue this one as well for running. Let's work on the interpreter. So we have two methods here. One is for running inferencing, and it returns the predictions. And then the second method is checking the predictions. Actually, this is different. Sorry. This one is actually doing inferencing against the same image but with different models. Okay, this is for testing one image, and this one is for evaluating the whole model. And if I look at the examples I had here, so I should have some examples of how to call it. Let's just copy and paste one. For now, just as is. So test model, so TFLite model file, which will be saved as a variable here. Yeah. And then I don't know what the index is. This is basically actually for, because test images is a list, and I'm just saying what's the index of the image that we're interested in. And what is test images? I don't know where test images is coming from. I think I need to test images. Define it somewhere. So this is what I did. I just got a batch actually this is as numpy. So I got a batch of 32 images from a dataset, and I set it into a variable, so that's all it is. This is probably not very efficient. And it always changes. But I'm just running as is for now. Still I think don't forget to click the like button if you're still around. Waiting until it completes. I think it's almost finished. If I can also make this faster by some optimization code, I'll look into that the next time. Okay, it's finished. Now I should be able to call the next code. Actually, no, this is for. I'm going to comment that out. Let's run the inferencing against one image at least. Yeah, so we are using the TFLite model now, and we've actually got it right. So the prediction says cat, the ground truth also says cat, so it's correct. So let's just swap. Oh, by the way, I need to comment this out, otherwise it keeps swapping between different images. So if I try number 4, it predicts a fox, and wow, this is good. 2. Yeah, the predictions are good in general. Maybe because not bad. Okay, this gives me like a very like this is a good indication, but it doesn't tell me how accurate the model is. So what I need to do is call the second method, evaluate model. For TFLite, the evaluation is a bit more complicated. So I'm going to call, in fact, I'm going to copy and paste the evaluate method call I did the last time. I'm just going to copy this. Yeah. And I'm going to finish here just to, you know, it's getting late, but you know, I think I've already accomplished the main objectives for this live stream, which was to add the code that converts to Tensorflow Lite. So this method here is evaluating the model against all the test data set. It should give me like an actual accuracy at the end. Debug, because I was doing a lot of debug before. Probably need to disable it, to be honest. I get all these prints? Not sure why I get so much debug. So much that I can't even get to the end. So evaluate model. TFLite model is here. This is where all the print statements are. Yeah, so still it's almost right. So you can see the normal TensorFlow model actually has an accuracy of 43%. It might seem low, but actually this is almost the same as the full TensorFlow model. So the accuracy is expected, to be honest, to be as low as that. To be honest, I thought it would be worse. So it's we're doing experiment 5, right? So it's a little bit worse than the full TensorFlow model. Well, actually, it's the same almost. It's almost the same. Okay. So it's almost the same. So this is for the normal TensorFlow Lite. Let's try against the one which is from the Edge TPU. Yeah. The one that we can use with an Edge TPU, the fully quantized model. So TFLite. I think the variable name is somewhere here. Let's see how well it does. If I was running now this in the Edge in the TPU, right, it would run faster because it is in a format that the TPU prefers. Everything is integers, so it can do very fast mathematical operations. A bit slower, as you can see, than the other model because yeah, I'm almost done. You can actually save this as a copy again at the end as a GitHub JSON, and you'll be able to refer to this and try it yourself. I might not actually wait until it completes. It's a bit late. So I can't comment anymore. Hello, hi Agent Smith. Now is a good time to ask questions if you have any, since I'm waiting for this to complete. I bet if I run this in the Edge in the TPU on this runtime, it should be a lot faster. But I don't want to swap now. Uh, yeah, I think I'm still continuing with this. The next stage for this project, actually, I think I've gone as far as I wanted in terms of training the image classification model, right, with the data that I have. And the next step is actually going to be maybe more interesting. I'm going to actually I'm going to review some of the code I already wrote for the Raspberry Pi. It's already in GitHub. I've written in the past some code to run a TFLite model, right, on the Raspberry Pi, and I wanted to see. But before I even do anything with that, actually, I need to define the architecture. And this time I want to actually treat all these models as APIs. So this model itself, this model I've developed, is going to be an API that I can call with from within the Pi. Okay, so it's finished. I'm a bit surprised. The accuracy is actually higher for the fully quantized model. Okay, so to answer in short, dark matter, right? For tomorrow, I'm going to continue with something related to the Raspberry Pi wildlife camera, but I'm going to transition to a new phase of the project, which is to define the architecture of the code I'm going to write for the Pi. I'm going to have a bunch of microservices running inside Docker, and then I will have something calling the APIs. And the idea is I don't want to, for example, I don't want to call the image classification model without using, for example, something which is called MediaPipe from Google. I don't know if you heard MediaPipe. This is a toolkit that you can use. It already has some out-of-the-box machine learning models, so I can use this to do just I don't know, person detection or very basic detection, and then I'll call my Pi. All right, okay, I'm going to finish the stream now. Thank you so much for joining me today, and I'll see you again soon.